All right, so now we're going to take a look at some trends and a couple other properties of the elements in the periodic table. The first one we're going to take a look at is the trend in ionization energy, which we often abbreviate as IE. And what is ionization energy in the first place? Well, this is defined as the energy needed or required to remove an electron from the atom in the gas phase. Okay, so because energy is needed, this is going to be an endothermic process. All right, and that means then your energy here is going to be positive. You have to provide that in order to remove that electron. The valence electron, as you can imagine, being the outermost electron, is the easiest to remove. So it's going to have the lowest, it's going to require the smallest amount of energy. Okay, so the first ionization energy is the energy required to remove the outermost electron from a neutral atom. We abbreviate first ionization energy as IE subscript 1. So if we have a metal, which we will just designate as M in the gas phase, we need to provide that ionization energy in order to get rid of that electron. So if we take away an electron from M neutral, we end up with M with a positive 1 charge. All right, that's what the first ionization energy is. If we take that resulting ion and we remove a second electron from it, then we would need to provide the second ionization energy to get rid of that second electron. We end up with M with a 2+ charge, right? So this would be the second ionization energy, or IE2. As the second electron is removed here. And we can continue doing that over and over again. We can take that M2+ now in the gas phase. We now provide some energy to remove that third electron. We end up with M with a +3 charge, and we eject that electron. All right, so this would be the third ionization energy, which means the third electron is going to be removed. So we need to know what ionization energy is first before we talk about the trend. Okay, so we have those ionization energies plotted here on the y-axis in units of kilojoules per mole, and we plot that as a function of increasing atomic number, going from left to right. So what you'll see is, first of all, as we go from left to right across the table, the types of elements that have the highest first ionization energies are all here at the top. Those are the group 8 elements. Those are the noble gases, right? These have the highest first ionization energies, and the elements with the lowest first ionization energies are down here. These all belong to the group 1A elements. These are the alkali metals. These have the lowest first ionization energy. So what does that mean? A low ionization energy means you don't need a lot of energy to remove that electron, whereas a high ionization energy means you need to provide a lot of energy to get rid of that electron. Right? And there's a general trend as we go across from left to right, the ionization energy increases. Right? As we go across the periodic table, the ionization energy increases, and then when we get to a new row, it just drops all the way back down, and that repeats itself periodically. So why is that? Well, going from left to right, we know, or we've seen across a period, the ionization energy increases. So why is that? Well, we can use the Z effective nuclear charge. We've seen that it increases in that direction. Right? And what that means is as you go across the period, the electrons, those valence electrons, are held tighter to the nucleus. And if they're held tighter to the nucleus, it requires more energy to remove them. Right? That just makes sense. And as a result, the ionization energy going across the period increases. Going down a group, okay, down a column, what we will see is that the ionization energy decreases. It takes less energy to remove that outermost electron, and we can explain that because the effective nuclear charge also decreases down a group. So as you go down a group, because the effective nuclear charge decreases, those outermost electrons are not being held closely or strongly to the nucleus. It is very easy to remove them. So we don't need to provide a lot of energy to get rid of those electrons. So the ionization energy goes down as we go down a particular group. All right, so we can plot that. We saw the table. We can plot it this way as well. All right, so going across a, going down a group. So if we look at group 2, for example, okay, you can see the bars decrease as we go down, and that's the general trend. What you may see is going across the period, going this way, for example, we said the trend was going across from left to right, the ionization energy tends to increase. But you will see a couple exceptions to that. So for example, if we look at the period 2, lithium, beryllium, boron, carbon, nitrogen, oxygen, and fluorine, you can see boron, for example, has a lower ionization energy than beryllium, and oxygen looks like it's got a lower ionization energy than nitrogen. So why are there those exceptions to that general trend that we talked about previously? Well, we can explain that due to the types of orbitals that are there, and also due to the type of shielding that's going on. All right, so for example, if we compare the beryllium and boron, and we look at their electron or orbital diagram, we can see we can compare them, and it looks like this, right? So beryllium's on top, boron's on the bottom. So if we talk about the ionization energy for beryllium, we're looking to see how much energy we need to remove this electron. Okay, so the energy required to remove that electron compared to boron, the amount of energy needed to remove that electron. That's the ionization energy that we're looking at and we're comparing. Which is easier to remove? Well, this one here in the 2p, it's easier to remove, and the reason is that one is being shielded by those core electrons over here. Right, so it's not experiencing a full nuclear charge pull towards the nucleus. Whereas in beryllium, okay, that electron is actually part of the core electrons. And because of that, it's harder to remove. So the ionization energy is higher compared to, for boron, where you have that that one electron there that's in the p that's being shielded. We'll also see, if we compare nitrogen and oxygen, we'll see something similar occurring. So in nitrogen, this is our electron orbital diagram, and in oxygen, we can compare them. So the only difference between N and O is this electron here, that's in yellow. All right, so one thing to keep in mind is when you have a half filled, where all the electrons are all spin up or all spin down, so a half filled sublevel is actually very stable. Compared to this case here, where this electron actually introduces a little bit more instability, so it's easier to remove that electron. because that leads to something being more stable. Whereas if you try to remove, let's say, this electron here in nitrogen, because you're pulling it away from something that is already really stable, it's going to take more energy. So as a result, the oxygen is going to have a lower first ionization energy compared to the nitrogen. So we can use not just shielding, but we can use the stability of our orbital diagram to help explain that phenomenon. So we've seen the trends in the first ionization energy. We can also look at the trends in successive ionization energies, and we can make some conclusions based on what we observe. So for example, if you look at sodium over here, we have the first ionization energy as 496 kilojoules per mole, and then there's this huge jump to the second ionization energy. And similarly for magnesium, the first two, we have a low first ionization energy, a low second ionization energy, and then there's this huge jump to the third ionization energy. So whenever you see huge jumps between ionization energies, that usually means that we're getting now to the core electrons, because the core electrons are going to be way more difficult to remove than those outermost electrons. So core electrons are difficult to remove. They have very high ionization energy. So we can observe that for sodium, for example. We know sodium has one valence electron, and it's very easy to remove it. Right? It doesn't take a lot of energy, just 496 kilojoules per mole. But when we remove it now, the remaining electrons are all in the core, and it takes a lot more energy to remove that core electron. Similarly, magnesium has got two valence electrons, so those first two ionization energies are really, really low. And once we remove them, we get into the core, and now for the third ionization energy, it has a very, very, very high value. So by looking at successive ionization energies, we can tell indirectly how many valence electrons are there, right? So that's something we can measure, and we can draw some conclusions based on what we observe. So the other trend we're going to take a look at is the trend in something known as the electron affinity. An electron affinity you can think of sort of as the opposite to ionization energy. It's the energy released when an atom in the gas phase attracts or gains an electron. All right, so here we have our element M, whatever M is going to gain an electron. Since we're sticking a negative charge, we end up with something with a -1 charge on it. And then that typically releases energy, which we assign as EA. So energy here is released. So as a result, that would be an exothermic process. So the change in energy there is going to be negative. And that's opposite to what we saw for the ionization energies. So the more energy that's released, the larger the electron affinity, and the more negative the number, the higher or larger the electron affinity. So what does that mean? Well, that gives you an idea of whether an atom really wants an electron or whether it really doesn't want it at all. All right, so the trend there is as we go across a period from left to right. And again, when we say across a period, by default we mean going from left to right across the table. Okay, we see that the electron affinity becomes more negative going from left to right. And that means that as we go from left to right, those atoms really, really want to gain those electrons, right? And if we compare the actual values, we'll see that the halogens, which are in group 7, okay, they have the highest electron affinities for any of the groups, right? So as you go across a period, going in this direction, right? Fluorine here has the highest electron affinity. So it really wants that electron. You'll notice that the noble gases, they have electron affinities that are positive. And what does that mean? Well, that means these are very stable, and we already established that the noble gases are very stable. They don't want any electrons. They are happy the way that they are. And if we were to add electrons to them, that would cost energy. So it costs energy to add electrons. So we need to provide energy, in other words, for that to happen. All right, and that's not very likely to occur compared to the other elements on the periodic table. Okay, so the last thing we're going to take a look at in this chapter is sort of a global view of the table itself. We introduced at the beginning of the chapter metals versus nonmetals as a way to sort of classify and separate the periodic table. So let's take a look at some of the characteristics of metals versus nonmetals. And generally, they tend to be opposite characteristics. So metals tend to be malleable, meaning that we can turn them into sheets. We can pound them into sheets, in other words. And ductile, meaning we can turn them into wires. Metals, as you probably know, are shiny. They're lustrous. They tend to reflect light. They're good conductors of heat and electricity. When they form compounds like oxides, for example, they tend to be basic and they tend to be ionic compounds. Metals tend to form cations, positive ions in solutions, and in order to do that, they tend to lose electrons, and as a result, they become oxidized. Nonmetals tend to do the opposite, right? They tend to be brittle in the solid state. They tend to be more of insulators, both electrical and thermal insulators. When they combine with oxygen, for example, they form oxides that tend to be acidic. And nonmetals tend to gain electrons to form anions, and when they gain electrons, they become reduced. So in terms of when we look at the table as a whole, in terms of the metallic character of the elements, we can describe that as the ability then of an element to lose electrons. So if an element is readily able to lose electrons, it has high metallic character. If it doesn't want to lose electrons, it's got low metallic character. And across the periodic table, the trend is actually really, really simple, right? So as you go from, and I'm going to change our arrows here a little bit. As we go from right to left, going this way, metallic character increases. And going from top to bottom, metallic character increases as well. So the general trend then is you go from the top right to the lower left of the table. That's how metallic character increases as you traverse the periodic table. All right, so metallic elements found on the left side of the table, these tend to be good reducing agents. They are easy to oxidize, which means they lose electrons easily. They are very reactive. They tend to combine with other things very easily. For example, they react with nonmetals to form different types of salts. And those compounds, they usually dissolve in water very easily, and you find them in things like seawater, for example. In terms of some of the physical properties, going down, or for the metallic elements, the melting points tend to decrease. Going down the columns, or the groups 1A and 2A, they tend to have very low melting points for metals. If you compare them to the melting points for things like, lead or copper, for example, the group 1A and 2A metals tend to have low melting points, relatively speaking. Going down the group as well, the densities tend to increase as you go down a particular group for the metals. So the very last slide here on this particular presentation is a good summary of some of the periodic properties. It gives you the trend going down a column, going across a row, but it also gives you the reason for the trend, which is really the most important thing.